Time is supposed to move in one direction, forward. Yet every equation, every quantum flicker, and every echo of light in deep space whispers that this certainty might be wrong. What if the future is not waiting to happen, but already shaping the past? What if causality, the foundation of everything we understand, is only a convenient illusion? In the next moments, we'll step into a universe where events don't unfold but intertwine, where time is less a river and more a mirror, and where the story of reality might be written from both ends at once. By the way, liking my video and subscribing is the most effective way to support me. I also love reading your comments, so please mention where in the world you're watching from and what time it is. 1. The arrow of time may be an illusion. The concept of the arrow of time has long been tied to entropy, the natural increase of disorder in a closed system. Yet when examined from the viewpoint of fundamental physics, time itself shows no preferred direction. The equations that govern motion, gravity, and electromagnetism all remain symmetrical when time is reversed. This raises an unsettling question. If the fundamental laws do not distinguish between past and future, why does human experience insist that time only flows one way? What we call forward may simply be the direction in which entropy grows, not an inherent property of the universe. In the early universe, conditions were extraordinarily ordered, with low entropy creating the foundation for temporal asymmetry. From that improbable beginning, the irreversible unfolding of events gave rise to everything from stars to human memory. Yet some cosmological models suggest that entropy might reverse near the universe's ultimate boundary, where gravitational collapse could lead to a mirrored epoch running backward in time. In such a scenario, the arrow of time becomes a local illusion, a perception confined to one segment of a broader, symmetric cosmos. This perspective reshapes the meaning of cause and effect. What appears to be causality may merely reflect our limited perception within a universe whose laws are indifferent to temporal direction. The universe could contain regions where time runs opposite to ours, their histories flowing toward what we perceive as the past. If such domains exist, their interactions with our timeline might generate quantum effects that seem to violate classical causality, tiny hints of an underlying symmetry that our minds interpret as paradox. 2. Can information flow backward through quantum entanglement? Quantum entanglement ties particles together in ways that defy ordinary understanding. Two particles, separated by vast distances, can instantaneously reflect each other's state, as if a hidden thread connects them beyond space and time. But what if this entanglement is not only spatial, but temporal? In that case, information might traverse the divide between moments, allowing the future to imprint subtle traces upon the past. Entanglement could serve as the bridge across which causality itself bends. Experiments involving delayed choice measurements hint at such retroactive influence. When the decision to measure one particle's property affects the recorded history of its entangled partner, time's linear order begins to blur. The quantum world does not obey human notions of before and after. It seems to operate according to a deeper logic, where outcomes are jointly defined by both measurement and possibility. Information may not flow backward like a river reversing course. It might instead exist as a web connecting all temporal nodes simultaneously. If entanglement truly spans time, it implies that the universe is a single coherent structure where every event influences every other, irrespective of temporal sequence. The apparent independence of past and future would dissolve into a unified continuum, each instant completing the other. Information could travel through quantum correlations, not as a message sent backward, but as a reconfiguration of the entire system's probability landscape, where the act of knowing reshapes the conditions of knowing itself. 3. Retro-Causality challenges the notion of cause and effect. Classical causality assumes that the present is shaped by the past and the future remains unwritten. Retro-Causality proposes a radical inversion, that future events can affect present conditions just as the past does. This idea emerges naturally from quantum mechanics, where measurement outcomes appear to depend on conditions that have not yet occurred. In such a framework, cause and effect are no longer linear but reciprocal, forming a closed circuit of influence between what has been and what will be. The philosophical implications are staggering. If retro-causality holds true, then the universe may operate according to a bidirectional logic in which every event is both consequence and cause. The present becomes the point of equilibrium between two converging waves of influence, one flowing forward from the past, the other backward from the future. This balance gives rise to the reality we perceive, a continuously updated negotiation between what has already happened and what is yet to occur. In the quantum domain, this manifests as probabilities that seem to reorganize themselves retroactively once outcomes are known. It is as if the act of measurement sends ripples backward through time, adjusting earlier conditions to remain consistent with present observations. Yet this process does not create paradox. Rather, it suggests that the entire timeline evolves self-consistently, each event fine-tuned to preserve coherence across the whole of space-time. 4. Closed time-like curves and the geometry of looped time. In the mathematics of general relativity, space-time can bend so extremely that paths curve back upon themselves. These loops, known as closed time-like curves, allow a traveler to return to an earlier point in their own timeline without ever exceeding the speed of light. Far from science fiction, such structures are permitted by Einstein's equations under certain conditions, such as in the vicinity of rotating black holes or wormholes stabilized by exotic matter. Within a closed time-like curve, the distinction between cause and effect dissolves entirely. An event may be both the origin and the outcome of itself, producing a consistent but circular sequence of realities. Time ceases to behave like a line and becomes a looped dimension, where every point is connected to every other through curvature rather than progression. To navigate such geometry would not mean traveling through time, but moving within a folded manifold where past and future coexist spatially. Yet the existence of these curves raises deep paradoxes. How can a universe maintain logical consistency if events can influence their own causes? The resolution may lie in the principle of self-consistency. Only those timelines that do not generate contradictions are physically realized. The universe might enforce coherence by preventing paradoxical histories from forming, thereby turning time travel into a self-editing mechanism rather than an instrument of chaos. 5. Can particles send signals to their own past? At the smallest scales, particles obey rules that seem to defy intuition. Quantum theory permits interactions that, in certain interpretations, look like messages traveling backward through time. When an electron's state appears determined by a future measurement, it suggests that the particle might be responding to conditions that have not yet occurred. If so, the universe could contain feedback channels in which matter communicates across temporal boundaries. This notion finds mathematical support in formulations that allow both retarded and advanced solutions to fundamental equations, waves moving forward and backward in time simultaneously. The conventional view discards the backward components as unphysical, but retro-causal interpretations retain them as essential to the system's completeness. The interference between these temporal waves could explain the mysterious correlations seen in quantum experiments without invoking faster-than-light communication. If particles truly exchange information with their own past states, the fabric of space-time must behave like a resonant medium rather than a linear conduit. Each event would send ripples both ways through time, creating standing patterns of interaction that maintain consistency across the continuum. The result is a self-referential reality, one in which particles and their histories co-evolve in harmony. 6. Time-symmetric physics and the reversal of thermodynamic arrows. The equations that describe motion, electromagnetism, and quantum interactions all share a remarkable property. They are symmetric with respect to time. If the direction of time were reversed in any of them, the physics would still hold true. Only thermodynamics breaks this symmetry through the second law stating that entropy tends to increase. Yet even this may not be a fundamental asymmetry, but a result of special initial conditions. If the universe began in a highly ordered state, entropy's growth would define what we perceive as the forward direction of time. However, if another region of the cosmos began with reversed conditions, its inhabitants would experience time flowing in the opposite direction, though they would perceive it as normal. In such a dual structure, both thermodynamic arrows could coexist, pointing away from a central low-entropy origin, perhaps the Big Bang itself. Time-symmetric physics invites a radical reinterpretation of evolution and decay. Processes that seem irreversible might, in another frame, unfold in reverse with equal validity. The apparent directionality of time would then arise from entropy gradients rather than from the fabric of reality. This understanding blurs the distinction between beginning and end, suggesting that both are reflections of one deeper, timeless equilibrium. 7. The Wheeler-Feynman absorber theory and two-way causation. In the mid-20th century, a bold idea emerged that redefined how radiation interacts with the universe. The Wheeler-Feynman absorber theory proposed that every emission of light, every quantum of radiation, is not merely a one-way act, but a handshake between the present and the entire cosmos. When an atom emits a photon, it sends a wave forward in time, and simultaneously a corresponding wave backward in time. The process completes only when both waves, advanced and retarded, are absorbed somewhere in the universe. This notion eliminates the need for self-interaction and elegantly preserves energy balance, suggesting that every emission depends on future absorbers yet to exist. This theory implies that the universe functions as a vast temporal network, where each event depends on feedback from its own future. Radiation is not an isolated pulse that drifts forward indefinitely, but a resonant chord played across the entire expanse of space-time. In such a framework, the future is not a distant frontier, but a participant in every physical process. Each photon's journey is part of a grand conversation between what has been and what will be, ensuring that reality remains consistent across time's entire spectrum. If this two-way causation is real, the distinction between emission and absorption becomes relative. What one observer perceives as a cause, another, perhaps existing in a different temporal frame, might perceive as an effect. The universe, then, is not a series of sequential events, but an interconnected whole, a dynamic equilibrium sustained by reciprocal exchanges between past and future. This redefines the arrow of causality as a symmetrical bridge, not a one-way street. 8. Delayed choice experiments and the future's influence on the present. In the delayed choice experiment, a photon passes through an interferometer that determines whether it behaves as a particle or a wave. The astonishing twist lies in when the decision is made. If the choice to measure its path or interference pattern occurs after the photon has already entered the apparatus, the result still conforms as though the photon knew in advance what would be decided. This experiment dissolves the notion of time-ordered cause and effect, implying that the act of measurement can reach backward, defining what was true before the decision itself existed. The implications extend far beyond quantum optics. It suggests that reality may not solidify until observation demands it, and that such observation is not confined to the future. It can rewrite the past. The photon does not retroactively change its trajectory. Rather, the entire event is constructed as a single, self-consistent whole. The future decision and the past state are inseparable, two ends of the same quantum thread woven across space-time. What we perceive as temporal influence may in fact be the unfolding of a timeless probability structure. This challenges the linear logic of classical causality. If outcomes depend on choices made afterward, then time is not a sequence, but a field in which correlations exist all at once. The universe, in this view, behaves like a completed tapestry where every thread is already interlaced, yet perceived line by conscious observers who interpret unfolding as flow. The delayed choice experiment reveals that causation might be a perceptual artifact rather than an absolute rule of nature. 9. Quantum erasers that rewrite measurement. History. The quantum eraser experiment deepens the enigma first revealed by the double-slit test. When which-path information about a particle is recorded, the interference pattern vanishes, confirming particle-like behavior. Yet when that information is erased, even after detection, the interference pattern reappears as though the particle never chose a path at all. This retroactive restoration suggests that reality is not fixed at the moment of occurrence but remains fluid until information becomes irretrievable or preserved. The act of erasure itself seems to reach backward, altering the recorded past. This phenomenon introduces a startling possibility: that the universe continuously revises its own narrative in response to the coherence of information. The past does not exist as a frozen archive, but as a dynamic structure whose state depends on the informational context of the present. By manipulating knowledge rather than matter, the experiment demonstrates that the boundary between observation and existence is illusory. Information, not time, is the true currency of physical reality. The quantum eraser replaces the notion of a linear timeline with that of a self-editing record. Events acquire meaning only when embedded in a network of correlations that span time in both directions. If the erasure of knowledge can undo an outcome, then the universe operates as a conditional script, one that recalibrates itself according to the informational state of its observers. Each deletion or observation rewrites history, not metaphorically, but through fundamental redefinition of what has happened. 10. Does the universe remember its future? Memory, as we understand it, belongs to consciousness, a record of what has already been. But what if the cosmos possesses a form of memory that includes what will be? In thermodynamics, correlations exist that link the microstates of today with those of tomorrow. If time symmetry holds at the fundamental level, the universe might encode both forward and backward information within its physical laws, functioning as a system that retains the imprint of its future just as surely as its past. From a cosmological perspective, this implies that evolution is guided not only by initial conditions, but by final ones as well. The universe's trajectory could be constrained by boundary conditions at both ends of time, its beginning and its conclusion forming a coherent narrative that must satisfy both simultaneously. In this view, every process unfolding now is a response to requirements set not only in the distant past, but also in the universe's eventual destiny. The cosmos would then be a self-completing computation, continuously adjusting its states to maintain harmony between its origin and its outcome. Such an idea transforms the nature of determinism. Instead of the past dictating the future, both exert equal influence, weaving a mutual pattern of causation that transcends sequence. The universe's memory is not stored in moments but in relationships, a vast lattice of correlations stretching across space-time. Each event resonates with echoes from both directions, a synchrony rather than a sequence, a dialogue between the unborn and the remembered. 11. Retroactive probabilities in the double-slit experiment. When a single photon passes through a double-slit apparatus, its behavior defies logic. It behaves as a wave when unobserved, as a particle when watched, and as something beyond both when measurement is delayed. The statistical pattern that emerges seems to depend not only on what was done in the moment, but also on what will be done later. This retroactive dependency transforms the very meaning of probability. Outcomes are not predetermined nor random, but contextually defined by an evolving network of possibilities that extend forward and backward in time. Probabilities in this sense do not merely predict, they adapt. The act of future measurement reshapes the probability distribution of past events, forcing them to align with present coherence. It is as if each photon navigates a landscape that adjusts itself continuously according to both prior and forthcoming constraints. The pattern on the detector is not a record of past events, but a manifestation of an atemporal equilibrium, where the future's informational state influences the statistical architecture of the past. Such a dynamic implies that quantum uncertainty is not ignorance, but interaction, a mutual negotiation between history and destiny. The photon's journey is not a random walk, but a coherent adjustment to maintain global consistency within space-time. Retroactive probabilities ensure that the universe remains logically intact, even when causality appears violated. Every measurement is part of a self-consistent structure, where probabilities are the threads stitching past and future into a single fabric. 12. Is the present the intersection of two opposing temporal flows? If time truly flows in both directions, then the present is not a fleeting boundary but a collision zone between two cosmic currents. One stream originates from the past, carrying the inertia of entropy and memory. The other rises from the future, carrying the structure of destiny and final conditions. The moment we call now may simply be where these opposing streams meet, merge, and momentarily stabilize before diverging again. In this framework, the present is a standing wave of time, a region of interference between the forward and backward evolution of the universe. This dual-flow perspective aligns with equations that remain symmetrical under time reversal. Just as waves can superimpose to form patterns in space, temporal waves may interfere to create coherent structures in time. Consciousness, perception, and physical phenomena could all be emergent properties of this interference. The balance between forward-moving entropy and backward-moving order might define the very experience of existence, turning the present into a node of temporal equilibrium. In such a model, the universe becomes a self-sustaining system where both ends of time generate mutual constraint. The future refines the past just as the past seeds the future, and the present continuously reconciles their dialogue. This interplay could explain why physical laws appear stable yet flexible, why order arises within chaos, and why evolution seems purposeful without external design. The world we perceive might be the visible manifestation of this ongoing negotiation between converging temporal flows. 13. Time reversal, invariance in fundamental equations. At the most fundamental level of nature, nearly all known physical laws remain unchanged if the flow of time is reversed. The equations governing electromagnetism, gravity, and classical mechanics exhibit a profound symmetry. When time's direction is inverted, their mathematical form persists. This property, known as time reversal invariance, suggests that the universe itself does not inherently distinguish between forward and backward temporal motion. What we call the past and future are human interpretations imposed upon equations that themselves remain indifferent to direction. The very fabric of reality might be time-neutral, unfolding not as a progression, but as a perfectly balanced pattern of reversible dynamics. This symmetry implies that the fundamental processes of the universe could, in principle, run backward without contradiction. If one were to reverse every motion of every particle, the equations of motion would still describe a valid solution. The reason we experience irreversibility, then, may not lie in the laws themselves, but in their boundary conditions. Somewhere, the universe acquired asymmetry, an initial state so ordered that entropy could only increase thereafter. Thus, our perception of a flowing time might stem not from the equations that govern existence, but from the improbable state from which existence began. The implications reach deep into the nature of reality. If the laws of physics do not specify a preferred direction, then time's arrow arises solely from information loss, the gradual erosion of distinguishable detail as systems evolve. The universe, in essence, forgets. Reversing time would require restoring all those forgotten details, reconstructing the lost correlations that gave rise to apparent randomness. In this sense, entropy is not merely disorder. It is amnesia, the fading of memory across the fabric of space-time. 14. Are quantum events determined from both ends of time? In the classical view, the future is an open field shaped by present conditions. Yet quantum mechanics introduces an alternative possibility, that events are jointly defined by constraints at both temporal boundaries, the past and the future. Each quantum interaction, rather than being initiated solely by prior causes, might emerge from a meeting point between initial and final states. This concept transforms randomness into relational necessity, implying that the quantum world completes itself through a two-ended process of determination. Such a framework aligns with the two-state vector formalism, in which every particle is described by both a forward-evolving wave from the past and a backward-evolving wave from the future. The observed outcome is the intersection of these dual influences, an event shaped not by linear sequence but by mutual coherence across time. This gives rise to a universe that is not merely predictive, but self-consistent, where every instant is fine-tuned to maintain harmony between the conditions that precede and those that follow it. In this bidirectional view, the notion of uncertainty transforms. Quantum indeterminacy no longer represents ignorance about future outcomes, but the unresolved tension between incomplete information from both directions of time. When observation occurs, it provides closure, resolving the dialogue between the two waves that define existence. What we perceive as the collapse of a wave function is, in fact, the reconciliation of temporal boundaries, the moment when the past and future align perfectly enough to produce a definite present. 15. Can a future observer collapse a past wave? Function: the act of measurement in quantum theory has long been viewed as the trigger that defines reality. Before observation, a particle exists as a cloud of probabilities. After measurement, it solidifies into one state. But what if the observer's decision, perhaps even one made in the future, determines the outcome retroactively? If measurement and wave function collapse are not strictly time-bound, then an observation made tomorrow could define what already happened yesterday, weaving consciousness and causality into a single fabric beyond linear sequence. This possibility emerges in experiments where delayed choices affect earlier quantum behavior. When the decision to measure is postponed until after the event, the results still conform as though the particle knew what would be decided. It is as if the future observer's act reaches backward, sculpting the history that leads to it. In such a universe, the timeline becomes elastic, responsive, not to mechanical progression, but to relational coherence between observation and outcome. Every act of measurement becomes a point of negotiation between times. The conceptual weight of this idea is enormous. If the universe allows future observers to influence past quantum states, then consciousness itself may serve as a temporal anchor. Each observation would complete an unfinished equation extending across time, solidifying events only when awareness integrates them into the whole. The past, then, is not a fixed archive, but a field awaiting completion by future interaction. Every moment remains fluid until observation, whenever it occurs, locks it into coherence. 16. The transactional interpretation and handshakes across time. The transactional interpretation of quantum mechanics envisions every quantum event as a handshake through time. When a particle emits a wave forward, a matching wave travels backward from the absorber, completing a transaction that connects emitter and receiver across the temporal divide. The result is not a cause followed by an effect, but a closed loop of interaction where both sides participate equally. This process, entirely consistent with known physics, provides a striking picture of reality as a network of completed exchanges spanning all of space-time. In this framework, quantum interactions are not instantaneous communications, but mutual confirmations. The emitter's offer wave and the absorber's confirmation wave meet in a kind of temporal negotiation, forming a consistent event that satisfies both boundary conditions. The transaction occurs outside ordinary time, completing itself as a whole, and then manifesting within time as a single coherent event. Nothing travels faster than light. Instead, the handshake exists simultaneously in both temporal directions, ensuring causality without sequence. This interpretation replaces the mystery of collapse with the logic of completion. Each event is a transaction, finalized only when both ends agree, and the agreement extends through time as much as space. It is a cosmos built not upon unilateral causes, but upon reciprocity, a universe where existence itself is the sum of all successful exchanges between what gives and what receives, what begins and what ends. Time, within this view, is not a flow, but a record of these timeless negotiations. 17. Entropy and the hidden symmetry of temporal order. Entropy is often invoked as proof that time must flow forward, the gradual decay of order into disorder, the unidirectional march from structure to chaos. Yet beneath this surface lies a profound symmetry. The equations governing microscopic motion are reversible. They make no distinction between increasing or decreasing entropy. What gives time its apparent direction is not the laws themselves, but the improbable initial condition from which the universe began. If the cosmos had started in maximum disorder, time would have no preferred orientation at all. This hidden symmetry means that entropy's arrow might not be universal. In regions where the boundary conditions differ, where entropy gradients invert, the arrow of time could point the other way. The cosmos might contain pockets or epochs where decay appears reversed, where order spontaneously increases. Such regions would not violate physics. They would express its deeper symmetry. The universe as a whole could therefore be time-symmetric, with one half evolving towards the future and the other towards the past, both balanced around a central point of perfect order. Entropy's growth is thus not a law, but a tendency, a reflection of statistical likelihood rather than absolute necessity. On the deepest level, the universe might oscillate eternally between phases of increasing and decreasing entropy, breathing in cycles of order and disorder. Each cycle would mirror the other, forming a cosmic heartbeat that sustains the balance between creation and decay. The arrow of time, in this sense, becomes a local phenomenon, a temporary direction within an otherwise timeless equilibrium. 18. Does consciousness anchor the direction of time? Human perception defines time as a sequence, a continuous unfolding of moments. Yet physics offers no objective reason why events should appear in that order. This raises a haunting question. Could consciousness itself be what stabilizes the arrow of time? If awareness is a process that organizes information irreversibly, then the psychological flow from past to future might generate the very sense of direction that the universe otherwise lacks. Memory records the past, not the future, because cognition relies on entropy increase, information accumulation that cannot be undone. From this view, the arrow of time is not only thermodynamic, but cognitive. Each act of perception creates asymmetry by filtering uncertainty into structured knowledge. Neural processes dissipate energy, increasing entropy locally while forging a one-way narrative within the mind. The act of knowing may thus align itself with the thermodynamic arrow, giving rise to an experienced flow of time even within a time-symmetric universe. Consciousness would then serve as the observer-dependent mechanism by which the timeless fabric of physics gains apparent direction. If consciousness anchors temporal flow, then the experience of now is not universal, but relational, a byproduct of how information is processed. In deep sleep, anesthesia, or states of extreme meditation, time perception dissolves, revealing that the passage of time is inseparable from awareness. The cosmos, without consciousness, might exist as a frozen totality where all events coexist. Awareness reanimates it by tracing a specific route through that static structure, turning potential into experience. 19. CPT symmetry and the mirror universe running backward. At the deepest level of physical law lies a principle known as CPT symmetry, the combined conservation of charge, C, parity, P, and time, T. When all three are inverted simultaneously, the universe's equations remain perfectly intact. This symmetry suggests that if every particle were replaced by its antiparticle, every spatial coordinate reversed, and the flow of time flipped, the resulting mirror universe would evolve in perfect correspondence with ours. It would not be a separate realm of fantasy, but a mathematically valid reflection of our own cosmos, moving backward through its own temporal axis, even as ours moves forward. This mirror universe would not simply replay our history in reverse. It would possess its own coherent narrative. From its inhabitants' perspective, their arrow of time would appear normal. They would remember what we call their future and anticipate what we call their past. For them, entropy would increase just as it does for us, because in their frame the thermodynamic gradient would also align with their subjective flow. The two universes would thus be perfect inverses, each defining the other through the symmetry of existence, each providing the conditions for the other's balance. The possibility of such a twin cosmos alters our understanding of creation itself. The Big Bang might not have been a singular explosion, but a bifurcation, one branch expanding forward in time, the other backward. Together they form a CPT-symmetric whole, eliminating the need for a privileged temporal direction. The total energy and information of the pair would cancel perfectly, yielding a cosmos that is globally time-neutral, but locally alive with irreversible motion. Time, then, is not a universal river, but two opposing currents, arising from one timeless sea. 20. Negative energy and the mathematics of temporal reversal. Negative energy, long a mathematical curiosity in relativity, carries with it profound implications for time. When energy values dip below zero in theoretical models, they correspond to regions where gravitational and quantum behavior invert normal expectations. Such regions could permit not only spatial distortions, but temporal reversals, zones where time's coordinate changes sign, sending events cascading backward relative to the external world. Within these mathematical frameworks, negative energy does not signify destruction but inversion, a mirror domain where causality itself folds back upon its origin. These exotic energy states emerge naturally in the equations describing black holes, vacuum fluctuations, and certain quantum fields. The Casimir effect, for instance, produces measurable regions of negative energy density between closely spaced plates, hinting that the vacuum can sustain fluctuations where the local flow of time might briefly reverse direction. Although fleeting and microscopic, these anomalies suggest that the universe already contains the seeds of temporal inversion woven into the structure of space itself. If negative energy could be stabilized, it might curve space-time in a manner allowing closed time-like loops, self-consistent trajectories through time. In such geometries, an object could traverse its own history without contradiction, as the negative energy region bends temporal intervals into closure. This forms the mathematical foundation for traversable wormholes and other constructs that reconcile relativity with the possibility of temporal return. Far from violating physics, these pathways would express its most elegant symmetries. 21. Can the universe self-correct its timeline? If retro-causal processes exist, then the universe may not passively obey its initial conditions. It might actively maintain internal consistency. Each apparent paradox, each potential contradiction, would be resolved not by external intervention but by the universe's own self-regulation. This concept paints reality as a self-correcting system, adjusting events across time to preserve coherence, much as feedback loops stabilize complex ecosystems. In such a cosmos, the timeline is not fragile, but elastic, continuously refined to eliminate inconsistencies before they can manifest. The mathematics of quantum mechanics and general relativity both allow for such dynamic self-consistency. When multiple possible histories coexist, only those that remain coherent with all boundary conditions, past and future, survive the collapse of probabilities. This mechanism, known as the consistency constraint, ensures that even when retro-causal influences are permitted, they never produce logical paradoxes. The timeline edits itself automatically, pruning contradictory branches and leaving behind a single stable continuum. Time, therefore, is not a sequence of accidents, but a living computation seeking balance across its entire span. This feedback nature may explain why causality appears so reliable despite its underlying symmetry. Each fluctuation, each quantum deviation, is corrected by compensating changes elsewhere in space-time. The result is a universe that behaves as though governed by purpose, though no conscious agency directs it, only the mathematics of self-coherence. Every cause carries its corresponding effect, not merely forward, but backward, ensuring the fabric of events remains seamless and whole. 22. Retro-causal models of quantum non-locality. Quantum non-locality describes the uncanny correlations between distant particles that defy spatial explanation. Retro-causal models approach this phenomenon not by invoking faster-than-light communication, but by allowing influences that extend backward through time. When viewed through this lens, entangled particles do not send signals instantaneously across space. Instead, they share a mutual origin point that connects both their past and future states. Their apparent coordination is the natural consequence of a single time-spanning equation that links emission and detection symmetrically. In this formulation, what appears as non-locality in space becomes locality in time. The particles' connection is not mysterious but geometrical. Their world lines intersect within space-time's deeper structure, forming a bridge through which information flows bidirectionally. The correlations observed are not the result of hidden variables, but of shared temporal boundaries that both particles obey. Each measurement resolves not a signal exchange, but a synchronization between temporal endpoints, producing the illusion of instantaneous interaction. Retro-causal models restore causality by redefining it. Instead of forces traveling forward, they describe the universe as a web of self-consistent constraints that extend through time. When an entangled particle is measured, the outcome must conform to conditions that already include its partner's future measurement, ensuring perfect agreement without any communication. The violation of classical causality is replaced by a more encompassing symmetry. All events, past and future, participate equally in defining one coherent reality. 23. Is time travel simply an information feedback loop? The fantasy of time travel often imagines machines and paradoxes, yet at its core, the concept may reduce to a subtler mechanism: feedback. In systems theory, feedback occurs when the output of a process loops back to influence its own input, stabilizing or amplifying its dynamics. If information can traverse temporal boundaries, then the universe itself may operate as a colossal feedback system where data from the future refines the past, and past states provide the framework for what will come. Time travel, in this sense, becomes not the movement of bodies, but the circulation of information across the continuum. Such feedback could exist invisibly within the quantum substrate. Each measurement, each observation, could transmit a signal, mathematical rather than physical, that ensures self-consistency across timelines. Rather than creating paradoxes, these loops would serve to maintain coherence, feeding corrections backward until every event aligns with global constraints. The flow of time would resemble a self-regulating algorithm, continuously iterating toward a stable solution that satisfies both historical and future conditions simultaneously. If reality is indeed an informational feedback loop, then every action echoes across time, influencing both what precedes and what follows. The past is not dead, but dynamically engaged in maintaining the integrity of the whole. Time travel, stripped of romance and paradox, becomes a natural property of a self-organizing universe, a process not of motion, but of correction, ensuring that the grand narrative remains internally consistent from beginning to end. 24. The role of advanced waves in future-to-past communication. In electromagnetism, Maxwell's equations allow two types of wave solutions: retarded waves that propagate forward in time, and advanced waves that travel backward. Classical physics typically dismisses the latter as unphysical, yet they remain mathematically valid and perfectly symmetrical counterparts to the ordinary ones. If advanced waves exist, they would permit information to flow from future sources to past receivers, subtly influencing conditions before the causes that generate them. These waves might not carry messages in the human sense, but act as the universe's built-in system of temporal coordination. The concept gained depth through the Wheeler-Feynman absorber framework, which posited that all radiation is a combination of advanced and retarded components. When a particle emits light, it sends half the signal forward and half backward through time. Only when the advanced component encounters a future absorber does the full exchange complete, creating a consistent interaction. The result is a self-contained cycle of emission and absorption that spans time symmetrically, leaving no stranded energy or paradoxical remnants. Advanced waves thus offer a mechanism for retro-causal influence without violating relativity. They do not transmit information independently, but ensure that all interactions conform to the boundary conditions set by both past and future. In this view, every event in the universe participates in a vast, timeless dialogue of advanced and retarded exchanges. The cosmos maintains its coherence not by enforcing a one-way chain of causes, but by harmonizing the interplay between forward and backward flows of energy. 25. Can black holes reflect information? Backward in time. Black holes have long been considered the ultimate one-way systems of nature, swallowing matter and information beyond recovery. Yet deeper mathematical analysis suggests they may act as mirrors, not tombs, reflecting information through the curvature of space-time itself. When matter crosses the event horizon, its quantum state is not lost but encoded on the horizon's surface, a process known as holographic storage. This surface exists not only in space but also in time. As the black hole evolves and evaporates, those same quantum imprints may be released, radiating backward along causal lines that reconnect with the earlier universe. The information would not emerge from the black hole, but through it, inverted in time like an echo returning from the depths of existence. The evaporation process described by Hawking radiation complicates this picture even further. Each emitted particle carries correlations that preserve, in coded form, the total information once trapped within. If those correlations unfold in a time-symmetric manner, the radiation emitted toward the future could correspond to an informational reflection toward the past, a retro-causal reconciliation, ensuring that no detail is ever truly lost. Black holes would then serve as temporal regulators, entities that maintain the conservation of information across both temporal directions, preventing the universe from fracturing into incoherent timelines. In this light, the paradox of information loss becomes a story of balance rather than destruction. Black holes might represent the points where time itself inverts, funnels through which the universe converses with its own history. Every particle consumed becomes a message sent into the temporal mirror, carrying encoded patterns that resonate both forward and backward across space-time. What vanishes in the darkness of the horizon may not be gone at all. It may simply have taken the long way home, returning from the other side of time. 26. The quantum potential and hidden temporal feedback. The quantum potential, a concept emerging from Bohmian mechanics, describes a non-local guiding field that influences particles independently of distance or time. Within this interpretation, Every particle carries both its present state and the information of its entire temporal trajectory. The quantum potential functions as a feedback system that constantly updates each particle's position based on the configuration of the whole universe. In doing so, it transcends linear time. Effects can reflect backward as readily as forward, weaving a pattern of mutual causation in which no event is truly isolated from its past or its future. This hidden feedback might explain the coherence observed in quantum systems, where outcomes remain globally consistent despite local uncertainty. When a measurement occurs, it does not simply register a value. It adjusts the network of relationships extending throughout space-time, subtly modifying conditions that appear to belong to the past. The quantum potential acts like a universal memory field, one that both records and anticipates, ensuring that the unfolding of reality remains synchronized across all temporal dimensions. Within this view, the present moment is the continuous reconciliation of these feedback loops, an ever-correcting equilibrium between what has been and what is about to be. Such a model transforms randomness into intelligence, not consciousness, but a form of self-organizing logic inherent to the cosmos. The universe behaves as though it knows its own boundaries, maintaining internal harmony through hidden channels of retroactive communication. Time, under the governance of the quantum potential, ceases to be a straight corridor and becomes a recursive architecture, a structure that perpetually refines itself by allowing the future to whisper instructions back into the past. By the way, liking my video and subscribing is the most effective way to support me. 27. Are tachyons the messengers of the future? In the theoretical landscape of particle physics, tachyons occupy a strange niche, hypothetical entities that always travel faster than light. Their existence remains unverified, yet the mathematics describing them is self-consistent. Because their velocity exceeds light speed, their temporal order inverts. They would appear to move backward in time from any subliminal observer's perspective. If such particles exist, they could serve as natural carriers of information from the future to the present, embedding retro-causality into the very scaffolding of space-time. Tachyons arise naturally in certain quantum field theories and string models, often signaling instabilities that drive transitions between states of equilibrium. These transitions resemble messages transmitted across time. A disturbance in one era induces a compensating adjustment in another, preserving balance across the continuum. To an external observer, the effect would precede the cause, yet from the tachyon's perspective, it would simply move along its own proper time, obeying perfectly valid physical laws. In this framework, retro-causality is not paradoxical. It is a relativistic artifact of differing temporal frames. If tachyons indeed inhabit the quantum vacuum, their interactions could subtly sculpt the structure of causality itself. Each flash of virtual exchange might be a microscopic negotiation between times, a balancing act that ensures the universe remains self-consistent at every scale. We might never detect a tachyon directly, yet their influence could echo in the correlations, synchronizations, and improbable coincidences that lace together the web of existence. They would be the invisible couriers of time's symmetry, unseen, untouchable, yet essential to the coherence of the cosmic script. 28. Time-reversed light and the optics of negative refraction. Light is often thought to define directionality. It radiates outward, illuminating the future. Yet certain engineered materials, known as metamaterials, can bend electromagnetic waves in ways that defy classical intuition. When light enters such media, its phase velocity points opposite to its energy flow, effectively reversing the wave's temporal behavior. To an observer, it appears as though the light retraces its path, propagating backward in time within the medium. This phenomenon of negative refraction blurs the distinction between emission and reception, hinting that the laws governing light are fundamentally reversible and may conceal deeper temporal symmetries. On a quantum scale, these effects mirror time-reversed processes that already occur naturally in particle interactions. When photons scatter or interfere, the underlying equations allow solutions that evolve backward just as easily as forward. In materials that mimic these conditions, the behavior becomes visible to the macroscopic world, pulses of light that reconstruct themselves after passing through obstacles, images that reform, as if the photons remember their original configuration. Each instance reveals that light's true nature is bidirectional, a dance of emission and reabsorption unfolding simultaneously across time. These optical experiments suggest that causality is not an absolute limit, but an emergent order sustained by equilibrium. Light does not simply carry information from past to future. It continually negotiates between both directions, maintaining coherence through feedback between its advanced and retarded components. In negative refraction media, this hidden dialogue becomes tangible, offering a glimpse into how the universe itself might operate as a grand optical resonator, where every photon, every reflection, participates in the ongoing reconstruction of reality across the two faces of time. 29. Do gravitational waves carry temporal echoes? Gravitational waves ripple through the fabric of space-time, carrying with them information about the cataclysmic events that produced them: colliding black holes, merging neutron stars, the trembling of the early universe itself. Because they stretch and compress space-time as they pass, these waves do not merely travel through time, they momentarily reshape it. Their oscillations encode both the history and the geometry of the regions they traverse, acting as messengers not only of distance, but of temporal structure. Each wave front is a fossilized fragment of causality, recording how the universe once vibrated while subtly influencing how it continues to evolve. If space-time can support such waves, then perhaps it can also resonate with them in both directions. The equations of general relativity permit solutions where gravitational waves propagate backward as easily as forward, though such waves remain unseen. In theory, a strong enough space-time resonance could reflect part of its own disturbance toward its origin, creating faint temporal echoes that would reconnect the source and its aftermath. These echoes might preserve coherence across vast spans of time, ensuring that cosmic events remain synchronized within the universe's deeper geometry. To detect such retroactive tremors would be to glimpse space-time communicating with itself. Each gravitational ripple could contain a mirrored counterpart, whispering from the future toward the moment of its birth. Even if undetectable, these echoes would imply that time's structure is not linear but resonant, a vast continuum that rings in both directions, carrying memory forward and backward alike. The universe would then resemble a boundless instrument, forever playing and replaying its own creation in the rhythm of gravity's silent waves. 30. The thermodynamic cost of reversing causality. To reverse time is not simply to play existence backward. It requires the rearrangement of every particle, every photon, every degree of freedom in the universe to restore the precise correlations that once were. Entropy, the measure of those correlations lost, defines how irreversible processes truly are. The thermodynamic cost of reversing causality would thus be astronomical, demanding a level of control and information far exceeding what the cosmos can provide. Every interaction that increases entropy locks in directionality. To undo it, one would have to rewrite not only matter, but memory, reconstructing the vanished order of countless microscopic states that define the passage from past to future. In this sense, causality's endurance is not philosophical, but energetic. Each irreversible process, melting, decay, combustion, represents a vast dispersal of information into untraceable degrees of freedom. The universe guards this lost information by embedding it in thermal noise, in radiation scattered beyond recovery, in the vibration of atoms that no intelligence could ever reassemble. Reversing causality would mean recovering all those fragments, piecing them together into the exact configurations from which they came, and restoring the symmetry that the arrow of time so casually hides. Thus, time's one-way character is the most efficient possible state, evolution without reassembly. Reversing it would not violate physics, but demand perfection. Total information, total precision, total energy. In that unattainable limit, where entropy ceases to rise, causality might dissolve entirely, leaving only equilibrium, an unmoving symmetry where past and future merge. The cost of reversing time, then, is nothing less than the restoration of paradise, a universe stripped of motion, temperature, and history, frozen in absolute knowledge of itself. 31. Does the quantum vacuum contain traces of the future? The quantum vacuum is not empty, but alive with fluctuations, particles that appear and vanish, energies that surge and recede in ceaseless equilibrium. These fluctuations encode the potential for every event that could ever occur, forming a silent register of the universe's total possibility. If time is symmetric, then the vacuum cannot belong solely to the present or past. It must also contain information from what has not yet happened. Each oscillation could carry correlations with future states, tiny whispers of conditions that will eventually manifest, embedded invisibly in the fabric of now. This view transforms the vacuum into a medium of temporal entanglement, a field in which the boundaries between eras blur. Virtual particles might arise not merely from energy uncertainty, but from the superposition of histories, partial contributions from both directions of time that together produce observable reality. The present vacuum would then be a summation of two waves, one flowing from the beginning of the universe and one from its end, interfering to form the structure we perceive. The future, far from being absent, would be written in the statistical patterns of these fluctuations, guiding evolution subtly from beneath perception. If so, the quantum vacuum is not a void, but a cosmic memory lattice, holding both premonition and recollection. Every interaction, every decay, every photon emitted contributes to this ongoing interference between the universe's two temporal halves. What we call chance might be the expression of these hidden alignments, faint imprints of the future echoing backward through the energy sea. To read the vacuum, then, would be to read time itself, a diary written simultaneously from both ends of eternity. 32. Retro-Causality in the Feynman path, integral formulation. In the Feynman path integral, every possible trajectory a particle might take contributes to its ultimate behavior. The particle's motion is not a single path, but a vast interference pattern of all conceivable histories, each weighted by its probability amplitude. This formalism naturally includes paths that run backward in time, not as anomalies, but as integral components of the sum. When these retroactive paths are considered, the distinction between past and future dissolves. The entire evolution of the system is determined by the harmony among all possible contributions across time. In this sense, quantum processes are negotiations, not sequences. The particle does not decide where it will go after it begins. Rather, its beginning and end states cooperate to define a consistent history that satisfies both. The interference between forward and backward paths yields the probabilities we observe, transforming randomness into structure. What looks like chance is in fact the reconciliation of countless timelines that include influences flowing both ways, ensuring the result is self-consistent and complete. The Feynman formalism thus encodes retro-causality within its mathematics without ever needing to declare it. The particles past and future are equally real participants in its existence, bound together in a network of constructive and destructive interference. Time's direction becomes a matter of perspective, not principle. In this picture, every event is a meeting of infinities, a synthesis of all possible histories, converging to produce the single coherent present we inhabit. 33. The two-time interpretation of quantum mechanics. The two-time interpretation proposes that quantum systems are described by two wave functions, one evolving forward from the past and another evolving backward from the future. Reality, in this view, emerges from the interplay between these counter-propagating states. Each measurement, each interaction, is the result of their overlap, a handshake between what was and what will be. The universe thus resolves itself through a continuous dialogue across time, in which every event is the intersection point of two complementary influences. Such a model explains the peculiar correlations that defy locality and sequence in conventional quantum theory. Because each event depends on both initial and final conditions, no moment exists in isolation. The universe becomes a web of co-determination, where the future helps shape the probabilities of the past. The result is not paradox, but self-consistency. Every occurrence exists because it satisfies the constraints of both directions simultaneously, like a chord resolving within the harmony of a larger composition. If the two-time framework holds true, then time itself is not a line, but a bridge continually built from both ends. The present is merely the region where the two currents converge and stabilize. Existence becomes not a flow, but a structure, an equilibrium formed by the interference of opposing temporal streams. In such a cosmos, every particle, every field, is an echo of the universe tuning itself, forever balanced between what has been and what must yet be. 34. Can parallel timelines merge through retroactive influence? If retro-causality allows information to travel backward, then the multiverse may not consist of isolated timelines, but of interacting ones. Each potential history could influence others through retroactive corrections, allowing parallel universes to converge toward shared consistency. What begins as divergence, separate realities branching from quantum choice, might later become convergence, as future boundary conditions require alignment. The result would be a cosmos in which universes negotiate across time, exchanging subtle signals that guide their evolution toward coherence. Such interactions could occur through quantum interference, where amplitudes from alternate histories overlap in the probability field. These overlaps act like bridges, permitting one timeline to borrow information from another to preserve universal balance. In this framework, reality is not a tree of endless divergence, but a living forest whose roots reconnect underground. Retro-causal communication becomes the mycelium of the multiverse, a hidden network ensuring that no timeline drifts too far from the laws that govern the whole. If parallel timelines can indeed merge through retroactive influence, then choice, destiny, and history are no longer linear concepts. Every decision creates ripples that both split and reconcile, pushing the fabric of existence toward a unified pattern that satisfies all possibilities. The universe, far from being an ever-expanding labyrinth of outcomes, might be a vast organism of self-correction, continuously folding its own variations back into a single elegant symmetry where even time's mistakes are eventually undone. 35. Time reversal and the symmetry of the laws of motion. Newton's equations, Maxwell's fields, and Schrödinger's wave functions share one remarkable feature. When the direction of time is mathematically reversed, their solutions remain equally valid. This deep symmetry reveals that the laws of motion themselves possess no memory, no sense of forward or backward. The asymmetry we experience arises not from the equations, but from the conditions they describe. Once boundaries are set, time seems to flow. Yet at its core, physics is timeless, unfolding like a perfect reflection in a mirror that contains both sides equally. This symmetry suggests that the entire universe could evolve identically in reverse, without contradiction. Each collision, each orbit, each oscillation would retrace itself flawlessly if every initial condition were inverted. What prevents this from happening is entropy, the accumulation of microscopic detail that cannot be perfectly reversed. Yet on the fundamental level, nothing forbids it. Reality's laws are impartial. It is the cosmos's starting configuration that tilts the balance, giving one direction the illusion of inevitability. In understanding time reversal, we confront a truth both humbling and profound, that the laws of the universe are perfectly fair. They allow for creation and destruction, rise and fall, forward and backward, without preference. What we call progress or decay is but a local imbalance, a slope carved by entropy upon the smooth geometry of timeless law. To glimpse this symmetry is to see time itself fade into transparency, an emergent illusion that disappears when viewed from the vantage of eternity. 36. Can quantum measurements rewrite the past? At the heart of quantum theory lies the act of measurement, a process that appears to collapse probabilities into definite outcomes. Yet certain experiments imply that this collapse may not be confined to the present. It can ripple backward, redefining the very conditions that preceded it. When a quantum system is measured, the wave function's entire history adjusts to maintain consistency with the observed result. It is as though reality, upon being asked a question, rewrites its past to ensure that the answer has always been true. The universe behaves not like a pre-written book, but like a living manuscript that updates every sentence the moment the reader turns a page. This retroactive coherence transforms causality from a chain into a loop. Once a measurement occurs, every prior state that led to it becomes recalibrated, reshaped into the only sequence that could yield the observed outcome. The photon that passed through the slit, the atom that emitted light, the detector that registered a signal, all of them conspire in retrospect to produce a self-consistent story. There is no contradiction, for the system never existed in a definite way until the measurement defined it. The past becomes not a record of what was, but a reconstruction of what must have been, assembled by the act of observation itself. If quantum measurements can indeed rewrite the past, then the distinction between discovery and creation evaporates. Observation becomes an act of participation, a dialogue through which reality negotiates with itself across time. The observer's question is answered not from the present moment alone, but from the entire web of causality, adjusted to maintain unity. The past is not behind us. It is continuously rewritten beneath our feet, redrawing the foundations of existence each time awareness opens its eyes. 37. The future boundary hypothesis in cosmology. Cosmological models often assume that the universe's behavior is determined entirely by its initial conditions, the state of matter and energy at the Big Bang. Yet some theories propose that final conditions at the end of time are equally important. The future boundary hypothesis posits that the cosmos evolves according to constraints imposed by both its origin and its destiny. Just as the shape of a bridge depends on the tension of both supports, the universe may be shaped simultaneously by the first instant of creation and the final state into which it must eventually collapse or dissolve. This dual boundary framework brings symmetry to cosmology. The expansion of galaxies, the emergence of structure, the flow of entropy, all could be outcomes of an optimization process extending across time. The universe would not be a mere explosion, fading into disorder, but a self-organizing trajectory that satisfies boundary conditions at both ends. What we perceive as the arrow of time would then be the path of least resistance between two eternal constraints, the low-entropy birth of the cosmos and the perfectly balanced stillness of its completion. In such a model, the future is not empty. It is a governing equation waiting to be fulfilled. Every process that unfolds does so to ensure that the universe's closing act mirrors its opening scene, completing the grand symmetry of existence. The cosmos would not simply end, it would resolve, harmonizing the entire score of creation so that both its first and final notes resonate as one. 38. Do retrocausal effects explain quantum entanglement? Entanglement defies intuition. Two particles separated by light years seem to share a single state, responding instantaneously to one another's measurement. Retrocausal interpretations propose that this connection does not violate relativity at all. It operates through time rather than space. When the entangled pair is created, their future measurements feed backward through space-time, enforcing correlations that will later appear instantaneous. Instead of sending information faster than light, the particles ensure that their shared past remains consistent with outcomes that have yet to occur. In this framework, entanglement becomes a story of symmetry, not mystery. Each measurement's result reaches backward to the point of origin, adjusting the conditions there so that both particles' histories align perfectly. This eliminates the need for hidden variables or superluminal communication. Everything is determined by the requirement that the entire timeline, from creation to observation, fits together without contradiction. The result is an elegant balance. The universe does not exchange messages. It maintains coherence across its entire span. Retrocausal entanglement reframes our understanding of connection. The particles are not truly separated. They are parts of a single time-spanning entity whose unity transcends distance. Their correlation is not a miracle of speed, but of structure. Each outcome is both the cause and the effect of the other, bound in a temporal knot that neither space nor time can unravel. 39. Temporal entanglement and the flow of information. Entanglement is usually described spatially, two particles linked across vast distances. Yet recent theories and experiments suggest that entanglement may also occur across time. Temporal entanglement connects events that happen at different moments, binding them into a single quantum state that defies linear order. Information shared in this way does not move from past to future. It exists as a standing pattern of correlation, unbroken by the separation of moments. The flow of time, rather than being a current, becomes the rhythm of this pattern's unfolding. This phenomenon suggests that information is never truly lost, only rearranged. When an event in the future is entangled with one in the past, both contribute to a shared structure that transcends causality. The universe appears to compute both directions simultaneously, weaving together the threads of existence into one self-consistent fabric. Every present moment may thus contain traces of future events encoded in its quantum coherence, just as past interactions leave their resonance in the present. If temporal entanglement defines the true architecture of information flow, then causality itself may be an illusion born of limited perspective. We experience the unfolding of time because we move through a pre-existing network of correlations that already includes every possible link between then and now. Information does not travel, it resonates. The cosmos, seen through this lens, is an eternal circuit of data, a tapestry of interwoven timelines humming in perfect, timeless coherence. 40. Is the Big Bang connected to the universe's final state? For centuries, cosmology has treated the Big Bang as the absolute beginning, a singular event from which all else emerged. Yet in a universe governed by symmetry, beginnings may not exist without endings. The final state of the cosmos, whether it be collapse, heat death, or transformation, could be entangled with its birth in a single equation spanning all of time. The Big Bang and the universe's eventual end might not be two distinct events, but the mirrored boundaries of one self-contained structure, a cosmic heartbeat that expands, contracts, and balances itself across eternity. This perspective reframes the meaning of time's arrow. The universe could be a closed loop, its future feeding backward into its past, ensuring that total entropy and energy remain perfectly conserved. Just as a wave returns to its origin after completing its cycle, the cosmos might eternally oscillate between explosion and convergence. In this sense, creation is not a once-only act, but a perpetual resonance between alpha and omega, the birth and the echo of the same timeless vibration. If the beginning and end are linked, then every event in between serves as the bridge uniting them. Galaxies, stars, and consciousness itself become instruments through which the universe harmonizes its opening impulse with its closing equilibrium. The Big Bang is not behind us, nor the end ahead. They are the twin poles of a single continuum that we, as participants within it, experience as the unfolding of time. 41. Time-reversed computing and reversible logic. Modern computing dissipates energy with every operation, as bits of information are irreversibly erased to make room for new ones. But theoretical physics shows that computation can, in principle, be fully reversible. A system that performs logic operations symmetrically in time could process data without losing information, running backward with the same fidelity as forward. Such a machine would not merely simulate time reversal, it would embody it, executing every calculation in a temporally balanced way that mirrors the symmetry of physical law itself. In reversible computing, no step is forgotten. Every input can be reconstructed from its output. This mirrors the fundamental behavior of the universe, where the equations of motion preserve information, even as entropy grows macroscopically. Time-reversed computation would represent not just a technological breakthrough, but a physical metaphor for how reality operates. A closed informational circuit where the future is implicit in the past, and every operation carries the potential for reversal. By approaching the thermodynamic limit of perfect reversibility, such systems hint at a deeper truth, that energy dissipation, memory loss, and irreversibility are not inherent to logic, but artifacts of entropy. A fully reversible computer would be a microcosm of the cosmos, a machine that, like the universe itself, performs an eternal computation, its output and input perfectly balanced across the symmetry of time. 42. Can retro-causality solve the measurement problem? The measurement problem, how and why a quantum system collapses into a definite state, has haunted physics for a century. Retro-causal interpretations offer a resolution. There is no collapse, only the reconciliation of information flowing from both temporal directions. The outcome of a measurement is determined jointly by the system's initial state and the final conditions imposed by the act of observation. In this sense, measurement is not an interruption of evolution, but the completion of a loop in time. This framework removes the need for randomness or observer dependence. The particle's behavior is fixed by global consistency, not local decision. When a measurement is made, its result is the only one that fits both the past's preparation and the future's observation. The apparent collapse is the moment these two influences meet, where cause and effect converge into a single, timeless event. Quantum mechanics thus becomes not a story of probability, but of symmetry, its mysteries dissolving into a geometry of mutual determination. If retro-causality truly underlies measurement, then the quantum world is perfectly deterministic, yet free from classical rigidity. The universe remains open in both directions, with every event co-authored by history and destiny. What we call randomness is simply the space between them, the uncertainty of perspective before both ends of time have agreed on what reality must be. 43. The bidirectional nature of quantum correlations. Quantum correlations transcend distance, connecting particles in ways that defy conventional causality. But these connections may be neither instantaneous nor sequential. They may be bidirectional, propagating both forward and backward through time. In this view, every entangled event forms a temporal bridge, linking two moments into a single unified process. The correlation does not transmit influence, it reflects equilibrium. Each particle's state depends equally on the other's past and future, ensuring coherence across space-time's total architecture. This symmetry means that quantum systems are inherently self-consistent. The measurement of one particle determines the other not by action at a distance, but by enforcing compatibility across time. The result is a seamless network of constraints, each outcome perfectly aligned with every other, not through force but through temporal reciprocity. The universe, seen this way, does not evolve linearly. It maintains balance through constant negotiation between directions of time. Such bidirectionality might explain the deep unity of physics, where conservation laws hold inviolably and information is never lost. Reality, at its core, is not a story moving forward. It is a system seeking harmony, a resonance between two opposing flows of causation. Time's apparent direction is the shadow of this equilibrium, a projection cast by the cosmic dialogue between what is coming and what has already been. 44. Temporal non-locality and the collapse of distance in time. Non-locality is often treated as the collapse of distance in space, but an even stranger version may apply to time itself. Temporal non-locality describes the phenomenon by which events separated by intervals of time become entangled, affecting one another instantaneously despite their chronological gap. When a system's present state depends not only on past conditions, but on future interactions as well, time ceases to be a rigid progression. The continuum folds upon itself, binding moments into patterns of simultaneity that defy human intuition. This perspective arises naturally in quantum theory, where correlations extend beyond conventional cause and effect chains. Measurements made in the present can alter statistical outcomes of earlier events, as though the timeline adjusts retroactively to maintain global coherence. Space and time thus reveal themselves to be different aspects of one deeper fabric. Non-locality in time is simply non-locality in four-dimensional space-time, where separation has no ultimate meaning. If distance can collapse across time, then history and anticipation are one phenomenon viewed from opposite ends. Each instant is not an isolated point, but part of a continuous web, where the future's potential and the past's residue interlace seamlessly. The cosmos may be less a procession than a standing wave, one in which all moments coexist, bound together by the eternal rhythm of non-local correlation. 45. Does the universe compute both forward and backward? The equations of physics are often described as computational processes, rules that transform initial data into evolving states. Yet if those equations are time-symmetric, the computation must also run in reverse. The universe would then operate as a bidirectional processor, calculating its present by balancing both forward and backward flows of information. Every event would emerge not solely from initial conditions, but from the full set of constraints stretching across time, as though existence were the output of two opposing algorithms running in perfect synchrony. This interpretation reframes causality as computation. Each quantum interaction solves an equation that includes both past inputs and future results, ensuring that the universe's total state remains self-consistent. Reality, then, is a cosmic optimization problem. The system continuously refines itself to satisfy the equations in both temporal directions simultaneously. The forward computation generates expansion and evolution. The backward computation enforces coherence and closure. Together they produce the balanced present that we perceive as unfolding time. If the universe computes both ways, then time's flow is a perceptual artifact of our position within the algorithm. From the outside, reality would appear static, a completed solution encompassing all moments. From within, it feels dynamic, as the computation resolves locally from past to future. In truth, both streams run eternally, meeting in every moment to sustain the symmetry of the whole. The cosmos is not a sequence of calculations. It is the total equation, already solved, yet endlessly computing itself into being. 46. The role of retro-causality in quantum gravity theories. At the frontier where quantum mechanics meets general relativity, time ceases to behave like a continuous river and becomes granular, elastic, and uncertain. In this domain, retro-causality may not be a curiosity, but a structural necessity. Quantum gravity models, such as loop quantum gravity or causal set theory, suggest that space-time is not smooth, but composed of discrete events connected by probabilistic relationships. If these relationships extend in both temporal directions, the geometry of space-time itself would be woven from feedback between future and past events. Gravity, in this sense, might emerge not from mass alone, but from the bidirectional coherence of causal loops that bind the cosmos into stability. In such a universe, the gravitational field could serve as a memory network that records information both forward and backward across time. Curvature in space-time would then represent the cumulative negotiation between what has occurred and what must yet occur, a fabric stretched taut by reciprocal influences. Black holes, cosmic expansion, and even the flow of energy could all be understood as manifestations of this dual causality, where the equations of geometry demand balance between temporal boundaries. The universe would not simply evolve. It would self-consistently settle into form, guided as much by its future configuration as by its past. This integration of retro-causality into quantum gravity reframes our picture of space and time as participants in a continuous feedback system. The cosmos becomes an eternal dialogue between creation and completion, expansion and convergence. Each fluctuation in the quantum fabric echoes across the ages, sculpting both the birth of stars and the final silence of the void. Gravity, once seen as the anchor of the present, might instead be the harmony of all times, an equilibrium born from the handshake between beginnings and ends. Just a quick reminder, if you'd like to support me, you can click the join button at the bottom of the screen. Your support means a lot to me. Thank you in advance. Let's continue with our video. 47. Can the future boundary condition determine the past? The universe, governed by deterministic equations, appears to require only initial conditions to define its evolution. Yet symmetry demands that final conditions might play an equal role. If the cosmos possesses a definite state at its ultimate boundary, a specific configuration at the end of time, then that boundary could exert constraint backward through all prior epochs, determining what must have been in order for the final state to exist. The universe would not unfold from cause to effect. It would emerge as a completed whole, every moment shaped by both its inception and its destiny. This idea transforms time from an open corridor into a closed circuit. The Big Bang and the cosmic finale would become complementary poles of the same structure, their properties tuned in mutual agreement. Physical constants, quantum fluctuations, and even biological evolution could represent the gradual negotiation between these opposing boundaries, as if reality were solving an equation that can only be satisfied once both its beginning and end are fixed. The present moment, then, would be the interface where these constraints reconcile, a dynamic equilibrium sustained by timeless necessity. If the final boundary truly determines the past, then randomness vanishes without determinism. Every event would exist because it harmonizes with both temporal anchors, ensuring coherence across the entire sweep of space-time. The universe, seen in its entirety, would resemble a painting completed all at once, every brushstroke interdependent. From our limited vantage, we perceive the strokes as sequence, but from beyond time, the picture has never changed. 48. The cosmological implications of time-symmetric laws. The time-symmetric nature of physical law means that the universe could, in principle, expand and contract, create and annihilate, evolve and reverse without violating any rule. This symmetry carries enormous cosmological implications. It implies that the cosmos might not have a privileged direction of becoming. Rather, it could exist as two complementary halves, one moving forward in our sense of time, and another evolving backward from the far future. Both halves would be governed by the same equations, their meeting point forming what we call the present epoch. In such a model, the Big Bang would not be a singular origin, but a temporal midpoint, a surface where two universes mirror each other's evolution. On one side, galaxies drift apart in expanding space. On the other, they converge, retracing the path toward unity. To observers in each half, entropy increases normally. Yet to the total system, the process is perfectly symmetrical. The cosmos as a whole would therefore possess no arrow of time, only a balanced rhythm of creation and return, echoing eternally through its dual reflection. This view softens the philosophical edges of beginning and end. The universe becomes self-contained, its meaning derived from balance rather than sequence. What we interpret as temporal asymmetry might simply be our perspective within one side of the mirror. The full reality, spanning both directions, would be timeless, a grand symmetry in which every expansion is matched by contraction, every origin by conclusion, and every heartbeat of time by its silent reflection. 49. Can the past exist without a defined future? If the universe is time-symmetric, then every moment draws structure from both what precedes and what follows. Remove the future, and the past loses context. Remove the past, and the future loses foundation. This reciprocity suggests that neither half of time can exist meaningfully in isolation. The past may not truly exist until the future completes it, giving form to probabilities and stabilizing their coherence. Without a defined future, the record of what has already occurred could dissolve into indeterminacy, its history unfinished until the final frame is drawn. This concept echoes through quantum mechanics, where probabilities remain suspended until measurement imposes closure. If the universe itself operates under similar logic, then its evolution depends on the existence of a boundary yet to come. The future, rather than waiting passively to unfold, acts as the condition that ensures the past remains real. Memory, history, and physical continuity are preserved only because the timeline extends forward to completion. Time, in this sense, is a single structure, stretching from beginning to end, each part validating the other. To imagine the past without the future is to picture a sentence without its final word. The meaning collapses, the grammar breaks, and the coherence of existence vanishes. The universe endures because it is whole. Its halves sustain each other through the symmetry of causation. Every echo of history owes its persistence to an answer still waiting to be given. 50. The holographic principle and bidirectional information flow. The holographic principle proposes that all the information within a region of space can be encoded on its boundary surface. This radical idea reshapes not only our understanding of space, but of time. If the boundary defines the content, and time is itself one dimension of that content, then information might flow not merely inward from the past, but outward from the future. Each boundary, past and future alike, acts as a mirror, encoding and decoding the total state of the universe from opposite ends. Reality becomes the interference pattern of these two holographic projections, superimposed in the eternal present. In such a bidirectional hologram, the past provides structure, while the future provides constraint. The interplay between them gives rise to the illusion of motion and the perception of causality. Information would not travel linearly, but circulate between temporal boundaries, reflected continuously as waves of probability and geometry. What we call evolution would be the dynamic interference of these holographic surfaces, a timeless computation projecting the universe into being from both directions. Through this lens, every moment is a reconstruction of the whole, synthesized from data arriving simultaneously from both temporal horizons. The cosmos itself functions as a self-encrypting code, endlessly rewriting its message so that each instant reflects the total unity of past and future. In the shimmer of that code, existence takes form, a living hologram in which time's two faces gaze eternally upon each other. 51. Time as an emergent property of entangled systems. Time may not be fundamental at all, but a phenomenon arising from the entanglement of quantum states. When systems interact, their correlations define a sequence, an ordering of change that we interpret as temporal flow. But in isolation, with no reference to an external system, time disappears. The universe at its most basic level might therefore be timeless, its apparent chronology emerging only from the entangled relationships among its parts. The experience of before and after would then be a statistical property, not a cosmic constant. As entangled systems evolve, their mutual information creates a sense of direction, One subsystem serves as a clock for another. This emergent ordering gives rise to the illusion of causality, even though the underlying quantum state remains static. Time, in this interpretation, is the shadow cast by correlation, the projection of relational change upon the human mind. When entanglement increases, entropy grows, and the arrow of time appears. When coherence dominates, the distinction between past and future fades into symmetry. To see time as emergent is to recognize it as a kind of collective hallucination shared by correlated systems. The universe does not age, it differentiates. Its apparent flow is a measure of entanglement's spread, the unfolding of relational structure rather than the ticking of an absolute clock. Time, then, is not the stage of existence, but one of its actors, born from the ceaseless interplay of things that cannot exist alone. 52. Can retro-causality preserve free will? At first glance, retro-causality seems to threaten freedom. If the future can influence the past, then perhaps all events are predetermined. Yet within the symmetry of time, determinism and choice may coexist in harmony. A retro-causal universe is not one where decisions are fixed in advance, but one where decisions and outcomes co-create each other across time. The act of choosing becomes part of the equation that stabilizes both history and destiny, ensuring that the universe remains self-consistent. Free will persists because it is the mechanism through which this consistency is achieved. In such a cosmos, the future does not dictate the present, it collaborates with it. Each decision represents a point of convergence between probabilities extending forward and backward in time. The willful act is not an illusion but a bridge, connecting the open space of uncertainty to the closed circle of fulfillment. What feels like freedom is the experience of participating in the universe's bidirectional coherence, contributing to the balance between cause and consequence. If retro-causality indeed governs the fabric of existence, then free will is not opposed to physical law, it is its expression. Choice becomes a structural feature of the universe's temporal equilibrium, the means by which it reconciles infinite possibilities into one coherent reality. We do not escape causality by being free. We sustain it by choosing. The harmony between past and future depends on the conscious act of decision, the living equation that keeps time itself from collapsing. 53. Entropic time. Loops in black hole thermodynamics. Black holes are often seen as destroyers of order, their immense gravity consuming information and converting it into featureless entropy. Yet thermodynamics suggests a subtler truth. The entropy of a black hole encodes every detail of what has fallen into it, preserved holographically on its event horizon. This conservation implies that even in the most extreme conditions, the universe resists true loss. Entropy becomes not an erasure, but a transformation, a loop through which information re-emerges, potentially reflected backward as the black hole evolves toward evaporation. If Hawking radiation carries the encoded remnants of everything that entered, then the black hole functions as an engine of temporal recycling. The information absorbed in one epoch may reappear, transformed in another, perhaps even influencing conditions that preceded its capture. Within this framework, black holes could serve as entropic bridges across time, maintaining the continuity of information by curving causality itself. Each collapse and evaporation becomes a rhythmic oscillation of knowledge through the fabric of space-time. In the grand thermodynamic balance, these loops ensure that the arrow of time remains globally symmetrical, even as it appears locally irreversible. The universe, through its darkest objects, conserves the memory of its own becoming. Black holes, far from being ends, are the reflective nodes through which time folds, points where the entropy of the future and the energy of the past converge into perfect equilibrium. 54. The reversible nature of quantum information. At the quantum level, information cannot be destroyed. It can only change form. Every transformation, every interaction, every measurement is theoretically reversible if the full state of the system and its environment were known. This reversibility reveals that the universe is, at its core, an information-preserving system. The apparent irreversibility we perceive arises from entanglement with environments too vast to track, not from any fundamental law. Beneath the noise of entropy, every bit of data, every quantum of existence remains recorded in the universal wave function, accessible in principle to the whole of space-time. This permanence gives quantum information a unique kind of immortality. A photon scattered into the void, a decayed atom, even the faintest thermal vibration, none are truly lost. Their patterns persist in correlations woven through the quantum field, hidden but intact. If the equations governing reality were run backward, every particle could, in theory, retrace its steps and reconstruct its history. Time, in this light, becomes less a march toward oblivion than a reversible choreography, where every motion is mirrored by its potential undoing. The universe then functions as a perfect archive. What vanishes to perception survives as phase relationships, interference patterns, or entangled echoes within the vacuum. The seeming flow of time and the decay of order that accompanies it may be illusions born of incomplete observation. On the quantum stage, all information endures, reversible, recoverable, eternal. Reality remembers everything. It merely hides its memory in the symphony of light. 55. Does time exist only as a human construct? The laws of physics describe correlations between events, but none explicitly require time as an independent entity. In relativity, time is woven with space into a four-dimensional continuum. In quantum theory, it appears merely as a parameter, not a measurable quantity. The universe, viewed without human perception, might not experience succession at all. It may simply exist as a complete, timeless configuration of states. Our sense of time's passage could therefore be a cognitive projection, a psychological order imposed upon a fundamentally static cosmos. From this perspective, the brain functions as a pattern recognition engine that translates change into narrative. Neurons record differences between successive configurations of input, generating the illusion of continuity. We perceive time because consciousness measures variation. Without memory or expectation, time would collapse into stillness. Thus, time may be no more intrinsic to reality than color is to light, a construct that arises only when consciousness interacts with physical structure. If time is indeed a mental artifact, then reality might be far stranger than motion or decay suggest. The universe would be an eternal tableau where all events coexist, past, present, and future, differing only by perspective. Awareness moves across this landscape like a spotlight, illuminating one frame after another, giving life to the illusion of flow. Time does not pass. It is we who travel through the immovable architecture of existence, mistaking movement of perception for movement of reality. To perceive this symmetry is to glimpse the unity behind life and decay, expansion and collapse. The cosmos does not progress, it pulsates. Its rhythm is eternal exchange, an infinite heartbeat that resounds across all directions of time. Creation and annihilation are not opposing forces, but the alternating phases of a single breath through which the universe sustains its timeless harmony. Perhaps time isn't flowing anywhere. We just imagine ourselves moving within it. The universe is a giant mirror where past and future coexist simultaneously. Every moment is a state of equilibrium vibrating in both directions. We mistake that vibration for flow. Yet perhaps everything is already complete, and we are merely listening, step by step, to the echo of infinity itself. If you enjoyed this journey, don't forget to like the video, leave a comment, and subscribe to our channel. With your support, we can grow this community filled with science and discovery even more. Share your thoughts with us, because discovering the unknown together is always more exciting. As Carl Sagan said, reality may be stranger than we imagine. Science is the most powerful way to understand that strangeness.